Okay. Hello, everyone. My name is Samuel Ojuri. Today, I'll be doing a presentation that is titled Explainable Real-Time Construction Forecasting via Hierarchical Partial Pooling and Time-to-Event models. This work was done in collaboration with researchers at Teesside University, Loughborough University, and TaperedPlus Limited. First, I'll start with the business challenge, which is why construction forecasting is difficult. Typical construction projects evolve over a long period of time, and it is difficult to predict the outcome at the start of the project. So this creates a big challenge, predicting the outcome of projects. We also have the challenge of fragmented operational systems, wherein we have various unstructured data sources that exist as the disconnected data silos. We also have the challenge of right-censored observations, where we have several open projects that cannot be classified as lost projects or be ignored in the statistical analysis, which will introduce some bias in the prediction outcome. Finally, we have the challenge of trust and explainability, wherein stakeholders want to know how the predicted outcomes are derived to help them adopt the predicted outcome. Next, I'll talk about the actionable output we focused on during the development of this work. We set out to predict a win probability, to predict the conversion of a sales opportunity within a specified forecast horizon. And we used the Cox proportional hazard models for this because it could handle open opportunities appropriately. Next, we set out to predict a gestation timeline, which is the number of days to invoice, essentially when looking at a project up to when it starts bringing in revenue. So we wanted to predict that using some percentile completion estimates. And we used the gradient boosted accelerated failure time model to achieve this. Finally, we looked at coming up with a priority score, which is a composite score of about from 0 to 100 to help to rank opportunities in the sales pipeline according to their level of importance for the stakeholders. And these used the survival probability prediction, the predicted gestation, which is the velocity, as well as the contract value to come up with these scores. And we wrapped all of this in an explainability layer using sharp attributions and using an LLM to explain this in natural language to stakeholders. Next, I'll talk about the end-to-end pipeline of the framework. The framework starts with a source system with various unstructured data sources. The data is preprocessed and fed into a data synchronization and engineering phase, where we applied some techniques such as feature engineering and adding some temporal features to introduce seasonality into the data. We also passed the data to a numeric baseline engine where we added some statistical techniques like exponential time weighting and hierarchical partial pooling before the final analysis using some statistical model, using a survival model to predict the win probability, and using an accelerated failure time gestation model to predict the gestation period. Finally, we used the priority score composer to generate the priority score mentioned earlier, and we underlined this with an explainability layer that used the natural language to explain the justification of the predicted outcome to stakeholders. Next, more details about the data set and feature engineering phase. We used over 4,500 sales opportunities over a 3-year period, and we used a 20% validation holdout, as well as a feature selection gate, where we use a forward stepwise additive model to make sure that the features being added to the model increase the discrimination. More details about the feature engineering pipeline. We categorized the opportunities into labels that help the analysis. We also use some temporal features, as mentioned earlier, to capture the seasonality within the data. We also classified the data into monetary bands and use some log transform to capture the skewed monetary values in the data set. And we did a chronological split to make sure that we prevent temporal leakage. Next, giving more details about the first methodology, which is hierarchical partial pooling. The challenge is that during aggregations for statistical analysis, some sparse segments can make raw conversion rates that are unstable or overconfident, which we introduced bias. So we use the hierarchical partial pooling because this helps to solve the problem by borrowing strength from less specific segments and adding this to a weighted average of the segment so that it can meet up with a specified effective sample size. And we also use the exponential time weighting to make sure that the current data weighs twice as much as old data. This is the backoff process that help to handle the sparse segments. We started with the most specific segment, and if there is not enough sample size, we backed up to a less specific project level, and then backed up to a broader project category level, and finally to the project type level to meet up with the effective sample size. Next, talking about the next methodology, we use the sensor-aware time-to-event modeling to handle open projects, because these open opportunities, classifying them as lost opportunities or ignoring them will create some bias in the prediction outcome. So we use the Cox proportional hazard models because it can handle this use case very well. And we use it to estimate the win probability at a specified forecast horizon, essentially answering the research question. Given that a project has survived to the current age, what is the chance that it converts before the end of the specified forecast horizon? And we also use the graded boosted accelerated failure time model to predict a gestation timeline, which is the number of days to invoice. We use the cat boost algorithm for this, and we did an estimation of three completion estimates in percentile, which represented optimistic, median, and conservative timelines in days. Next, giving more details about the transparency layer. We made sure we use a sharp attribution analysis to analyze the input features to know what each feature, to know what each feature is contributing to the prediction. And we passed all of this to an LLM synthesizer to explain in natural language for the stakeholders. And we also gave the LLM an opportunity to make a contextual score adjustment that is capped, making sure it does not override the underlying statistical prediction. And we make sure that we have all of these fully logged and available for stakeholders to improve transparency. Regarding the threshold that was set for the contextual adjustment, score adjustment by the LLM, some preconditions were set to make sure that we have enough statistical evidence before using a capped adjustment. Next, talking about the results, we had very impressive results from the survivor model. Essentially, it showed discrimination increased significantly towards a 20-day operational window, which supports decision making, where longer sales cycles are normal. In this use case, the typical sales cycle is several months. So that's why we have this kind of discrimination shown in the data set. And regarding results for the gestation model and some conversion speed stratification, the AFT model showed promising results as well. We came up with a median absolute error of about 25 days and a median duration of about 118 days for a typical project. And we also had the survivor model. Survivor model was able to separate conversion cycles into long, medium, short, and very short conversion cycles. And we also noticed that there was a velocity drift in the average project duration for the 3 years analyzing the data. So it reduced from an average of 144 days to 68 days by 2025. Next, more details about the ablation analysis, wherein we tested the various components of the framework, and we noticed that removing the censor-aware formulation created the most severe impact, which invalidated the survivor model significantly. And when the hierarchical partial pooling component was removed, it primarily degraded the segments that had less than 30 opportunities. And we noticed that when we removed the exponential time weighting, there was temporal drift, and it was not able to capture the velocity drift mentioned earlier. For example, the post-pandemic velocity drift. Next, talking about practical contribution of this framework, we were able to use right censoring from Cox proportional hazard model to correctly handle ongoing projects and not treat them as lost opportunities or ignore them in the analysis. And next, we were able to handle fragmented operational data, synchronizing various unstructured data sources into a single consistent store. And as well, we were able to handle sparse project segments in the analysis using hierarchical partial pooling and a 4-level backoff to stabilize the estimates to meet up with an effective sample size. And finally, we also were able to handle explainability and auditability using sharp-grounded natural language justifications that were explained using an LLM to stakeholders. And finally, the key takeaway from this work is that forecasting accuracy and explainability must be co-designed for adoption in construction operations. Thank you very much.
Thank you, Samuel. So we're taking question. Is anyone have any questions?